Okay, with that, I'll stop sharing this thing and running them securely, and then focusing on running notebooks on Expanse and give you some information about what we've been doing in this arena. Let's see. And so we'll talk about what does it mean to do interactive high performance computing. It's kind of an emerging area. It's always been needed, but now the tools and technologies through cyber infrastructure are more supportive of that. And notebook security, very important. And our solution for launching easily the secure notebooks with the reverse proxy service, and then a client for that service called Galileo, developed by Marty, who's here with us, and then some examples of notebooks if there's time. So a brief overview. Here's Expanse. By now you guys should be familiar with it, and if not, go back to earlier presentations in our HPC user training. At this point, I believe up to this week, all of the talks are online as an interactive video, and you can go back and scroll through presentations, look for texts that terms that interest you, and get more out of the recording. And I hope you guys can make use of it. But Expanse is an HPC system with multiple racks that we call scalable compute units. There's 728 compute nodes, 52 GPU nodes. Each of these nodes has 128 cores. The GPUs have 40 cores. So it's a big system, but it's not the biggest, and that's with an intent. Our intent is to support what we call the long tail of science in the terms of a Gaussian type distribution of the numbers of people running jobs that only use some average number of cores, as opposed to using 1 million cores, perhaps just 10 or 20,000 cores, which to me is still quite an amazing concept. So that's what Expanse is dedicated towards. And so part of our support is through we're supporting innovative operations, and interactive computing is right in there, which is the focus of this talk. I won't go into much more detail for time. So let's just talk about what is interactive computing. I don't know if you guys can see this little message here, but I apologize if you do. Interactive computing, you do it all the time. On my laptop, I have PowerPoint and Word and Mail. I'm running my PowerPoint presentation. I have some external windows connected to Expanse. I have a whole lot of applications running. And from a simple computer scientist perspective, that's interactive computing. Anytime you send a message to the computer and it reacts and does something for you, you're interacting with the computer. So it's pretty common. It's been around for years. The standards have been evolving, which is how we end up with desktop windows. All of that interactive computing domain supports what you're trying to do on your laptops. But in high performance computing, it's very different. And I'll show you an architecture diagram of what Marty refers to as the HPC ecosystem, and what's involved in doing HPC computing, and consequentially why it's a little more complicated than just running something on your laptop. And sometimes that can even be quite complicated. So we'll talk a little bit about that, but it involves real-time user inputs onto a compute node. And the compute node, if you go back and look at the picture of Expanse, these are the compute racks that have compute nodes on them. You're not touching it. You can't pick the one you want to be on. There's a queuing management system that takes care of all that. You can see my running jobs presentation from a couple of weeks ago. It's a little more challenging to have control over where you're running your jobs. So real-time input, for example, how do you visualize a petabyte of data? You aren't going to do that on your laptop. The data has to stay somewhere. Your visualization application has to run on some resource, and it has to know how to manage a petabyte of data in the back end. So the complexity is really high, in addition to the complexity of just getting on and learning how to run jobs. So we recognize that. And so we're trying to support interactive computing and simplify your access to it. And so today I'll focus on how we've done that for Jupyter notebooks, so that you're running them easily and securely. And it's like just running a regular application on your laptop. That's our goal, and we're trying to get there. So the kind of tasks you would perform are code development, applications with large data sets, and user inputs coming from interactive applications like notebooks, MATLAB, RStudio, and there's a lot of other ones, visualization apps. And then you might make an interactive input that ends up with something happening on another system remotely. So interactive computing application examples, like I just said, there's Jupyter Notebooks, and we'll burrow into that in more detail today. But also we support parallel MATLAB on Expanse. There's distributed Jupyter architectures for like Jupyter Lab and Jupyter Hub. And then visualization, ParaView is one of them, and VisIT, and we have one or two of them running. You can imagine it's quite complicated to do like parallel visualization. So accessing these compute nodes on Expanse, there's the first level is you log on into an X window, an X terminal window, and you log on and you want to try and run something on a compute node, like interact with a small code that you're developing, like Hello World. So you connect with the terminal, and the first thing you need to do is write a request to get an interactive node. We talked about that in the running jobs. So hopefully this is a little familiar to you. And so you end up, looks like this, you log on, you want to make sure, again, your environment is set properly, and then you run the command to get your interactive node. When it comes back, you'll notice I'm not on the login node, I'm on Expanse 955, and I can run OMP in parallel. So you can do it with all different kinds of applications. So that's interactive computing on an interactive node. You can do it for GPU. You want to make sure you are on a GPU node. So you might run the NVIDIA SMI command and see the output that confirms. So that's like the lowest level. And a lot of you will end up working at that level to compile or to do other things and tasks. Another way to get into Expanse and work interactively is through the Expanse user portal. It supports a lot of interactive applications natively. It will launch MATLAB for you. It will launch RStudio for you. And we've integrated the Galileo application and satellite reverse proxy service into the system, so it can launch notebooks for you. So you can just log into the portal and get all kinds of work done, running jobs, and this is interacting again with Expanse. And the portal really simplifies your life, especially if you're a newbie. You can start learning and run jobs and get a lot accomplished. I have a link to that down at the bottom of the presentation. If you have an Expanse account, you can get onto the portal with your Exceed portal, Exceed credentials. So I'll start burrowing down now into one interactive application that we found is very, very popular. Jupyter Notebooks are used on everything. So most of you probably already know what they are. You're using them in your classes, you're using them in your world. And I think that they've caught on because you're inside the application and you're making changes dynamically inside an application that you've run. And that seems to map well onto the mindset of scientists. So it's open source interactive web applications put out by the Jupyter community. And you can have several kinds of services. Notebooks, Jupyter Lab, which has a lot more features in it. It has Jupyter Notebooks. You can launch an X terminal. You can run all these other mini applications supported by it. And Jupyter Hub, which is a multi-user secured software system. It's got some gotchas that we don't allow the way it's currently installed. So we don't have Jupyter Hub on Expanse on purpose. And so part of the project that we've been working on is to help solve that. But the biggest vulnerability with a lot of the interactive services is they provide access to HPC file systems, in particular your account, often over HTTP, so it's unencrypted. So if you launch an interactive web service, be careful to make sure it's securely launched. Otherwise, you can get hacked. And we get hacked well, we don't get hacked. That happens very infrequently. We get probes and hits quite often and every day. And recently, a couple of Jupyter Notebooks running over HTTP were hacked. So that's why I'm talking about this project. I want you to learn that security on HPC systems is extremely important because it not only impacts you, it can impact everybody on the system. And by running these interactive applications, you're a vulnerability for hacking. You expose the system. So you don't want to be that person whose notebook, affected millions of people around the US. During COVID, over in Europe, a user's account got hacked and they brought down a whole network of COVID-related systems for doing computational chemistry. So be paranoid, but we do have solutions, and our help desk can help you if you are really concerned. So the services policies, we don't run any technologies that mount on the login node, like portals and Jupyter Hub. And we're working on ways to do them remotely. Expanse is an example where we took the OOD software, moved it onto a virtual machine, solved the security connection system. So now when you go into Expanse, you'll notice it's HTTPS, and you'll see that little lock symbol, and you'll have a secure connection. All of your messages are encrypted. So you can trust that Expanse gets you connected securely, just like SSH. So we just are very careful with what we allow on our systems. So use secure connections when you can. Use portal.expanse.sdsc.edu as well. So this is an example of a notebook running insecurely, and we're fixing that. So talk a little bit more about notebook security. There's a lot of ways to install and run notebooks. Usually you install Anaconda on your laptop and you run your notebooks locally, and I'll show you an architecture diagram that represents that. Remotely, you can install Anaconda on the remote machine, but note that when you're launching a Jupyter notebook, the default is HTTP, and we don't recommend that. And you can launch things more securely by going through some convoluted steps. Or you can choose what I'm talking about today to launch a secure HTTPS, that means it's encrypted, notebook service, a web-based service using our satellite reverse proxy service and the Galileo script. We recommend this. And I'll give you, it's available, it's easy, you just have to set an environment variable and use an example command, and your notebooks will launch securely. I'll show you that at the end of the talk. So you can run remotely over HTTP, that's the default. You can connect over HTTP via SSH tunneling, that's more secure but inconvenient, or use the reverse proxy service. You can launch Jupyter notebooks and services on CPUs and GPUs and on the interactive nodes, and you can use a Slurm batch script to launch things remotely. Treat that notebook URL that you get when you launch it like a password. So this is the ecosystem, and Marty gave a great webinar last December, and so I borrowed some of his architecture diagrams because they really clarify the complexity of the HPC ecosystem. You're at home on your laptop like I am today, and you might have a remote workstation or be on a workstation, and then through the internet, you're going to connect to the HPC system. It's got a lot of compute nodes, like I showed you in that picture. There's management nodes, there's the login nodes, which are not the same as management nodes or compute nodes. And there's an internal network that you'll be allowed on. So you can run jobs on these remote, on the interactive nodes. And then there's some shared files. So when you log on to Expanse, you end up on these login nodes. You don't initially end up on a compute node unless you get one through the interactive capability or through your the batch queuing system. And if you don't really know what those are, go back to the overview of running jobs where we talk about that in more detail. So to run locally, you install Anaconda, and when you run it, you get this local host connection with some token to make it unique, but you're in your own little ecosystem. And assuming your home network has not been hacked, that can happen, things are pretty secure. You can run jobs, look at your local laptop. A lot of machine learning people do that, a lot of other scientists, but at some point your laptop's not big enough and you have to move over to this architecture, an HPC system. So that can be a little painful. The other way you can, but this is using an HTTP connection on your own system. That example, here's just an example of using Anaconda. You launch Jupyter Lab, and through that you might launch a Jupyter Notebook, and you'll see some information telling you what your connection information is about. Notice that this is HTTP. Okay, so you can run over HTTP somewhat securely using remotely, sorry. This is an example where I launched the notebook on the remote machine. It opens up a port, it launches my Jupyter Lab or Jupyter Notebook over port 88, and when I put that into a web browser on my laptop, I'm connected to it, but it's still HTTP. It's not secure. So how do we make that more secure? That what we do is we have tunneling, SSH tunneling. So you have an SSH connection here, you create a port on, you open up a port on your laptop and a port on the remote machine, and create that as a tunnel connection. And then the HTTP messages go inside that tunnel pipe that you've made. And that's fairly secure. The problem is that you never know what port on a bigger, when you try to do it on an HPC system, you don't have control over those ports. You can also install a certificate, but that's a little complicated as well. So you want to run on Expanse. You need to run a notebook on Expanse on a CPU or a GPU. And we want you to be able to run securely, and we want to make sure that you realize when you log on, you need to do this on the login node, that connection, and then you'll get a compute node to run your job on. But you still have to have a secure connection for that compute node. And so first, there's a warning and a caveat. Whatever HTTP connection you get, don't run them on the login nodes. We'll shut that down. So you need to find ways to run things on the compute nodes, either interactively or using the batch script. But then we want to make sure that the URL, it's essentially a password. So you want to run it with HTTPS. So how do we do that? Well, we talk about this solution that we've been developing, the satellite reverse proxy service, and then a client called Galileo. Let's talk about what is the satellite reverse proxy service. Hold on, just close this. It's a system that allows you to launch your notebook or Jupyter Lab on any compute node. And we use a reverse proxy server, and I'll show you how that works. The notebooks are hosted on the internal cluster network. Let me just go to the diagram here. Oh, I'll show you in a second. And the service is available. It's launched internally on the internal Expanse network. If you go back and look at this diagram here, this is the internal network, but then it becomes made available to the user externally. So our goal is to make it easy for you to launch notebooks. You don't have to do a lot of software installation, and that it guarantees security. So by using our service, if it's easier to run a job, then you'll be more encouraged to use it. And it's designed to run on any HPC system, not just SDSC, but it has to be able to support Apache on the internal network. So there's two components: satellite, the service, and the client, which like Galileo, it's usually a shell-based utility that orchestrates the user's interactions. And you can find out more about that at the repo here. And these are listed at the end of the talk as well. What's a reverse proxy server? If you have somebody out on the internet or an application sending a request to some server, the server acts sort of like a firewall, manages the request, filters it, cleans it, manages the request, and then takes that material returned from, for example, a web server, returns it back to the person on the internet requesting it. The person doesn't talk directly to the web server. And so that's how the reverse proxy service works. So there's a little, this is a web sequence diagram that gives you an idea of how our clients work. There's other ways to make the client work, but this is what we're using right now, basically. you have a user who launches a script, you log in and you launch a script like Galileo, or you could make your own. Our initial one was called Start Jupyter. The script talks to the service and gets a token. And with that token, you build a URL and then submit a batch script to the Slurm scheduler to get a compute node. The Slurm scheduler returns a job ID, the user, we print that information out, and then we wait for that node to come, and we're monitoring the job status. Eventually, we get a node allocated, and the node launches the Jupyter Notebook, and the user gets this URL that's created as part of the script, posted in a browser, and then the satellite service updates the browser with status information. And when that notebook is, the node is available, it is allocated and launches the notebook, then the satellite reverse proxy service will send that information to the user's web browser running, user's web browser instance. So when we're using SRPS, you're going to log on to a login node. You're going to run your script, and the script will do all those things that I showed you in the sequence diagram. And this will be on the internal network, and the script will interact with the satellite reverse proxy service running on a management node. And the Slurm scheduler will go and find a compute node for you, launch the Jupyter Notebook, and the SRPS will know about this. And the user has a HTTPS URL connection that communicates with this SRPS, and you sit there and you wait, and when that notebook is up and running, then the notebook communicates with the SRPS server and sends signals back to the web browser. This all happens on the internal network over HTTP because we trust the internal network. We're working to move away from that a little bit, but that'll be next year. So what you need to know is you log on to Expanse, you run a script, a bunch of work gets done for you in the background, and you get a URL and you wait for the system to provide you with a secure HTTPS hosted Jupyter Notebook with an interesting URL where we've just taken some random words and put them together along with the token. So obfuscating the URL, but the real thing is that this is over HTTPS. But again, if you have your notebook running and you gave somebody that URL, then you've given them access to your accounts. And I'll show you an example, because when you launch a notebook, it goes and shows you a listing of Jupyter notebooks and the directory that it's in. So to work with this, we've been developing clients and working out what do the scripts do to interact with all those transactions, so we can hide all that from you. You can do SSH tunneling. You can go in and launch a notebook and maintain the tunnel and figure out the port numbers, but we've solved all that for you. The SRPS system randomly gets a port number for you, makes sure that it's available on the compute node, waits for the compute node and grabs a port that's available. And gives you a randomly generated, hard to make up URL. And all you have to do is run the request and then sit there and wait for your web browser to become a notebook, to host a notebook. And so this is a second generation shell script that Marty took to the next level, and it's called Galileo. And it does, it creates your batch script on the fly. It saves the batch script for you. It parses the command line and helps you load and customize environment modules. There's a lot of work that's done in the background with this bash script. So the key features are you don't have to install conda. If anybody here has installed conda on an HPC system, it can take an hour. It can take longer. It can fail because there's a lot of work on the file IO side and a lot of packages. It can take an hour just to install the packages needed. So you can customize your conda environment if you need, but by default, what Marty's done is designed a system that supports the most commonly used packages that we've seen clients use on Expanse, and we keep adding to that. So use the system-wide installation if you can, send a note to the help desk if you need a different package as part of the Galileo system, and keep your life simple so that you just have to worry about your notebook and is it working. And you can use it through it's used behind the OOD, the Expanse user portal. So the key features, you just use the Galileo launch script and you pass some arguments to it. And if you need help, all of the options, the account, the reservation, if you're using some reserved queue, the number of nodes, the memory, standard things that you would ask for an interactive command, you also would ask in this request. And if you have any particular environment variables, there's a default group that you might want to always pass. So it's a very flexible, and Marty's continually adding to the features. So basically there's about 4 steps required to run your job. You have to make sure that you have Galileo in your path. Galileo or galileo.sh both work. And if you don't, you want to export that path. You can do this in your .bashrc, for example, in your resource script that gets run when you log in. But if not, just type this. So now I'm able to find the command, and then I run a command you need to have an account, a valid one, and then some time limit. This is a very simple example, but I'm snipping out a lot of information. Galileo prints out a comprehensive feedback information, giving you status information for what you asked for. And those all get saved in a directory called .galileo in your home directory. So I get my Slurm job ID, and more importantly, I get this funny looking URL that I put into my web browser, and then I just sit there and wait. If I'm impatient, I can on the command line monitor to see, is my job running. Pending, we're waiting for us to get the node, and then for things to start up, software to start up, and then all of a sudden it's running. So at this point, I'm waiting in my browser. We have the satellite server pending page with status information, so you can see where you are in the process. For example, a GPU might take a lot longer than a CPU debug request. So keep an eye on this pending page. This is what you'll see in the browser. And then this is what you would see if you were monitoring whether or not the job is running or not. So this example for the carload spray koala Expanse user URL I just got, notice it's got that lock on it. That is good. This is HTTPS. It's secure and encrypted. So be careful though, if somebody got that from you, they could log in through this notebook. Remember, when you launch notebooks, you have direct access to your folder. It gives you a listing of the files. So it's got a lot of features that are rich and wonderful, but you have to be careful. So take care of that. If you're done working on your notebook, be sure to shut down and exit to make sure the service shuts down on Expanse and it shuts down in the browser. And so you can run Hello World or some other notebooky type thing. Over here, you can see that it's just beginning, it's in the queue, then it gets mapped. That's something happening inside the satellite reverse proxy service, and then it's ready to run. And at that point, your notebook or Jupyter Lab service will be running. So GPU is the same way. You just have to make sure in your command that you're mentioning that it's GPUs. A little caveat about the exact commands that I've highlighted. Sometimes they change. Sometimes little requirements might change. So if this doesn't work, go to the homepage for Galileo, and Marty always keeps the most current, and I've got links to it, the most current working commands for the minimal needed. And if you need something more complicated, you contact the help desk and they'll work with you on making it more powerful. But you can run notebooks on GPU as well. A bit of advice is when you are on a GPU, use a container. We found just over time that on GPUs running notebooks, containers help everything run better because you're absolutely guaranteeing the environment that your job is running in. instead of depending on you remembering all the little things that need to be up and running when you're on GPU as opposed to CPU, the container will take care of that. And the user support group, primarily Marty, they keep a suite of containers in CM shared apps containers directory. And if you need something different, get in touch with the help desk. But he's tried to have a very rich selection of containers. There's ones for machine learning and other application spaces as well. Okay, so this is the same thing. You get a notebook here. I have a little hello world for the GPU that just runs SMI. And yes, I am on a GPU node. I've guaranteed that by getting this output from my notebook. You can run notebooks from the portal, the Expanse user portal. This is just an example of a form input. And then when it works, I get a Jupyter session information that gives me back a web URL. If you make a typo in the input form or something like that, then you won't get this. You'll get an error code. So you have to make sure you're picking a singularity image and that you're asking for the right amount of memory and basic things like that. So if you find a formula that works for you, again, write that down, put it in a little note file so you can reproduce this every time you want to run a notebook. The job of the portal is not to run your notebook, it's to give you a web browser where your notebook can be accessed. And again, just like normal, here's my notebook that's running on Expanse, and you can see my home directory here. Okay, so we're getting to the next part of the talk, should be on, yeah, okay, so we're pretty much at the end of the talk, and the next part would really be to do a live demo, but those don't always work. Like the other day I was doing a talk and the login node was having trouble, so I couldn't even log on. It was pretty interesting. So I have some canned examples, of course. We have a collection of training notebooks. They're everything from hello worlds to very simple machine learning. We're integrating some parallel notebooks using MPI for Pi and Spark. And so mostly they work. We try and track them and make sure they're all working. But the idea is if you have hello world, like I just showed you in that example before, you run the notebook on a GPU and all it does is hello and hello world kind of thing and runs NVIDIA SMI. But if you can get that far, then you know that a complex system, that HPC ecosystem, you're in it and you got so far as being able to launch a Jupyter notebook. That tells you that a lot of the stuff you're trying to do is going well. And this is great. It's really important to be able to isolate if you're having a problem, where is it occurring? So at this point, once your web browser shows a listing of your notebooks, you know a lot of stuff is working. So if you try to run a notebook, it's probably something in your notebook that's not working, as opposed to all of those layers in the HPC ecosystem. So part of learning high performance computing and parallel computing is getting an understanding of what layer in the system is causing you a problem. And we're trying to work on making that kind of error messaging more robust in a lot of our services, but it can be even more complicated when you're running notebooks. Okay, so you can, and we don't recommend it, but there are times when you might need to have a customized environment. And we're working with Marty and Peter Rose are working together to make it a little easier to do it using YAML. But if you need to, you want to make sure you can see conda, and if not, you can load the modules. We recommend, where possible, use the SDSC software installed by the user support group. And if there's a problem with that, or it doesn't do what you need, then contact them. But in this example, you may pick a custom environment that you have to build on the command line, and then you would pass that to Galileo. So there are situations where that's needed. And so if you need to, go ahead and do it and then test it out. So here is an example of Anaconda and making sure that I've got access to the Jupyter command, for example. So that's a little reminder, but again, we we would prefer you start using our standardized software so we can make it better. But sometimes you just won't be able to if you're doing some cutting edge. Okay, so future plans, and then I'll go into a mild demo mode. So we're trying to generalize SRPS so it can run on other systems, especially ones not at SDSC. That's one of our goals in the next year, is to test out that concept. And then we've integrated it into the user portal, as I said. And then future plans include generalizing SRPS to support other X11 web-based services so that you can add other applications. So that's something in the future we hope to move to. And then development of other clients for other kinds of services. You can download the satellite Expanse. You can download the Galileo GitHub repository. I have links for all of that. So with that, I'll stop the show and then show you an example of, because I want to make sure it works, I'm on Expanse here, and here's the command from Galileo. It says launch. Here's my account number, what partition I'm going to use the shared. I just want one CPU. I don't need much, a couple gigs. I don't want it to run long because I'm just doing a demo. I'm loading some environment modules, sort of a default group. And then Galileo spits out some information for you. And again, this is all saved in a folder called .galileo. And then something about what LMOD had to do with my environment to make sure the environment that Galileo's launching your job in is clean and correct. Have a token, generating the launch script, submitting the script to Slurm, my Slurm job ID, and success. And then I've got a URL right there. So Apple Dropkick Garter. This is a random word dictionary that is used for the generating of these terms. They can look pretty funny, but they work. And so this is an example. Let's see, let me find my, there we go. Server connection error. So it was up and running, and then it timed out because it's been 30 minutes since I tried it. But you can see I had a notebook running. I could see some notebook examples. I've downloaded that repository. Feel free to download the notebook examples repository and use that code for starters. If you want to add something, let us know. Our goal, though, is to keep that repository clean in the sense that, you know, every year we test everything out and we make sure they're running. So with that, I can take some questions. I can try and run one live for you. So let's see if we can do that, a live demo. Again, we all know live demos often don't work. So I'm logged in. You guys already know how to do that. This is one of the habits I've got, is when something works, I save it. So I keep different examples, sometimes for an application, because there's so much to keep track of. I just keep the information in here to remind myself to set the path. So it's something I would advise you to do. I do that for my module environment. I do that for Galileo. But here's the command I used before. We're just going to hit return, and it looks like it's working fine. I have a job ID, so I can do SQ and see that it's pending. And so now I'll take my HTTP URL, copy it. Make sure you get that and don't lose it so that you can look for it again. And I'll just make a new window, hit return. And so now you see the satellite RPS is pending, which is indicated here as well. And basically the satellite RPS looks at the job status remotely and monitors your job for you. So you can be logged on. Sometimes it is annoying. It's like, how many jobs are running on the machine that it's taking so long? So I could look at all of them and see there's 6,187 jobs. Well, how many of them are pending? Look for pending. 2,700 are waiting, so I might wait a long time, I might not. It's in the queue. Okay, so the satellite database, now it's gotten mapped. That means I have a node allocated, and we should see something soon. It's just a matter of some communication between that compute node, the satellite reverse proxy service, the queuing system, everything getting launched, the notebook launching. So proxied, and there's my notebook. Voila. The live demo worked. And that's great to be able to show you guys live. So that's really how easy it is. The hardest part is as your job evolves, futzing with the Galileo command. But once you get that command, and again, if you have trouble, contact the help desk and ask for some help on that. And we track those requests. Any other questions? Can you share your notebook with your coworkers? No. You want to share your password with your coworkers? We don't want you to do that. You have to do it differently, maybe have them launch their own notebooks, but we don't want you sharing that password. We're working on a solution for the Jupyter Hub, but that's complicated. And there may be other ways, and Marty might speak on that if he knows of anything coming up where multiple users can share a notebook, but we don't encourage that at all. It's an important question.
No, it's essentially, right. I mean, you have to think about the URL that's generated as a password, as Mary is saying, right? So it's like, how do you send a password securely to someone else? So you start running into more security problems, right?
Right. So we're looking at how can we let you launch a Jupyter Hub service on Expanse? It's probably going to be done with something called a Kubernetes container, where that's even more encapsulated, but Expanse doesn't support them right now. However, Jeff Weekly talked about, when does he talk, or did he talk about the Pacific Research Platform project and using Kubernetes? So it's not here yet, but Jupyter Hub would be a multi-user environment, but we don't have and don't allow that solution yet.
By default too, I think even Jupyter notebooks themselves, if you try to log into the same notebook with someone's already logged in, you'll get rejected. You have to kind of jump through some hoops to make that happen, I think.
Right. Just curious, how many people use Jupyter notebooks? Show of hands. Yeah, I see a few. All right, well, if you have a question, I can hang around for a couple more minutes. Otherwise, let's let Friday get started. Thank you, everybody, for coming, and I hope this helps and that you find the SRPS Galileo system useful. And if you have feedback, please send it to us or make a note on the GitHub repositories. We'd love to learn from you how to make this better. So Shengji, your question, Anaconda is a software system that it's an open source project that is designed to install and support several applications. And they have a version of it that can install on a HPC system called Anaconda. And it supports the external connections. It has a larger suite of applications than just Jupyter Notebook, but that's one of its biggest applications. So on your laptop, you would download Anaconda for Mac or PC, install it, and open up the application. And if you look at my pictures, you'll see that. And then have it launch a Jupyter Notebook or a Jupyter Lab. It's made to run on your local system. Miniconda is pared down. They took away all the crufty Windows toolkits that are needed so that you install Miniconda on a cluster or a workstation, and it gives you the minimal tools you need and packages you need to A, run notebooks, and B, have the libraries that you need, like math libraries, NumPy, or other packages that you would need, visualization, graphing, plotting, fonts, whatever it is, math libraries, whatever you need for your notebook comes with Miniconda. But it can take so long on a system like Expanse. It's unbelievable. So we now use Galileo through the portal for all of our training classes, for example, because we can bypass all of that. That said, if you need to, because you're doing some customized application where you have packages that you're working with a project that's making their own, then you can build a customized Conda environment, and we're okay with that. And then pass that as a customized environment to Marty's script. So it's a little more work, but it's what you might have to do for your application. And if you get stuck on that, contact help@exceed.org and get some help getting that done. And okay, so okay, any other questions? Well, go forth, have a good week.